Greetings. Welcome, everybody. My name is Jacqueline Cochran, a power system analyst at NREL, and I am pleased to introduce this webinar on our modeling tool, Regional Energy Development System India, which we call ReEDS India. This data-rich tool allows users to evaluate low-cost pathways for India's future electric power system. The speakers today will be Amy Rose and Ilya Chernyakhovskiy, both power system analysts in the Strategic Energy Analysis Center here at the National Renewable Energy Laboratory. We have many researchers at NREL who are actively developing and applying the ReEDS tool, historically developed for the U.S. power system. The skills of these researchers are diverse, reflecting the diversity of skills needed to conduct long-term power system planning. We are excited to expand this tool to be able to conduct state-of-the-art analysis in India and make this tool publicly available so that others can use it for their own research. After my opening remarks, the agenda today will be organized in two halves. Amy Rose will provide a brief history of the ReEDS India model, describe how the tool has been used, outline core capabilities, and discuss where we are going with the model. Then we will pause for a short Q&A. Then Ilya Chernyakhovskiy will walk through how to actually use the model, how to access it, set it up and run on your own machine, and run different scenarios. We will have a second opportunity for Q&A then. Before I turn this over to Amy and Ilya, I want to announce that this webinar is being recorded and will be made available afterwards. Also, if you're having any audio issues, please try switching from computer to phone audio or vice versa. GoToWebinar has a help desk if you are having any technical difficulties. Finally, if you have a question, please submit it using the questions pane on your screen at any time. The panelists will answer as many questions as possible. And now I would like to introduce Amy Rose, who's an electrical engineer at NREL and was instrumental in making ReEDS India a reality. Most recently, Amy has worked closely with state energy planners in Tamil Nadu to inform investment pathways. Amy, over to you.
Thank you, Jacqueline, and thank you everyone for being here. I first want to start by providing a little context on how and why the ReEDS model was developed. In the late 1990s, Walter Short, the original developer of ReEDS pictured on the left, recognized that existing planning tools focused on representing conventional technologies and did not address the unique challenges related to integrating wind energy as well as the value that wind can provide to the system. And so Walter, with help from Nate Blair, pictured on the right, and some others, set out to create a new type of model, which they called the Wind Deployment System, or WINDS. And over time, the original WINDS model was expanded to capture the salient features of other technologies, including solar PV, concentrated solar, hydropower, geothermal, and energy storage, among others. And this expanded model became the Regional Energy Deployment System, or ReEDS. Since its development, ReEDS has been used for a diverse set of studies. And with each analysis, we continue to develop new capabilities with the model to answer emerging questions, particularly questions related to the integration of renewable energy. And over time, this method of incremental development led to a model that was difficult to maintain and difficult to adapt to answer new questions. And so in the fall of 2017, NREL embarked on a project to rebuild ReEDS from the ground up. And the result was a cleaner, more flexible model that we're calling ReEDS 2.0 that can be easily augmented and also used for a variety of different research questions. So what exactly does ReEDS do? ReEDS is a capacity expansion planning model that provides insights on how the power sector may evolve in the mid to long term and the key drivers of power sector change. It's an optimization tool that identifies the least cost mix of investments in generation, transmission, and energy storage to meet future system requirements. And these requirements can include requirements for energy and ancillary services, as well as policy and regulatory requirements. We use a reduced form or time slice based dispatch to simulate how these assets will be operated in the future. And we use a capacity credit and curtailment module to capture the variability of wind and solar and power system operations. We also use resource supply curves to capture the costs and constraints associated with developing certain technologies driven by the resource quality, land availability, and access to transmission. ReEDS can be used to answer questions from a variety of different perspectives. For policymakers, ReEDS can provide insights on how different policies, technological advances, or energy strategies may impact investments and operations. For system planners who are interested in better understanding the drivers of change in the power sector, ReEDS can identify a range of probable investment outcomes. And others can use ReEDS to identify areas for more focused research and support, or identify investment trends. At NREL, we recognized how influential ReEDS had been in transforming capacity expansion planning in the US to better represent renewable energy. We also recognized that India was at the forefront of a dramatic transformation, with the government of India pursuing very ambitious renewable energy targets. And so in 2018, with support from the US Department of Energy, the Hewlett Foundation, and SIF, we set out to create an India version of ReEDS. We updated the geographic resolution to reflect the regions, states, and union territories of India, and we adapted the model constraints to reflect the level at which operational, investment, and policy decisions are made and implemented in India. We also adapted the temporal resolution, designing new time slices to capture the diurnal and seasonal trends in electricity demand and wind and solar generation. And all other inputs, including costs, operating parameters, policy and regulatory constraints, were also updated to reflect conditions in India. NREL was well positioned to undertake this task because we've considerable experience working on power system questions in India. Perhaps the best known example is our partnership with POSICO to develop a detailed operational model of the Indian power system to answer questions around the 2022 renewable energy targets. Since this study, we've continued to engage with India across a number of different projects at both the central and state level, as well as an analysis with a regional focus. The ReEDS India model has already been used for a number of studies, including national planning studies, looking out to mid-century to see how the power system may evolve, and shorter horizon studies, where we linked our ReEDS planning outcomes with a detailed production cost model in Plexos to validate the operational feasibility of the planned power system in 2030. We're also working with individual states, beginning with Tamil Nadu, to conduct more detailed state-level planning, where again, we took advantage of the flexibility of ReEDS 2.0 to update the geographic and temporal resolution of the model, as well as update model constraints to better represent the Tamil Nadu power system. And we have ongoing work to identify investment opportunities for energy storage, not just in India, but across South Asia, and we're using ReEDS as part of this analysis. Now that you know a little bit more about what ReEDS does, I'll share some of the key outputs you can get from the model. The figures I'm going to show are taken from our national planning study through the year 2047. And my goal is not to go into these results in detail, but to showcase the types of outputs you can get from the model. The primary output is the evolution of installed capacity and the generation mix over the planning period. The plot on the top shows the installed capacity, and the plot on the bottom shows the contribution of different technologies to meet demand in every year. As the dotted line on the top plot indicates, in ReEDS you can incorporate both planned or committed capacity additions, as well as economic or endogenously determined additions. ReEDS also enables users to see these results with a high degree of spatial resolution. These maps show the location of different technologies in the year 2047, with the colors indicating the amount of installed capacity in each location. As I mentioned, we selected the spatial resolution for our study, but ReEDS is flexible enough to incorporate more or less geographic detail, with the trade-off being that the more detail you add, the longer it might take for the model to solve. The results also include power flows and investments in transmission between nodes. We use a simplified pipe flow or transportation model to represent power flows, which means the model ignores reactive power and Kirchhoff's current and voltage laws. We assume power flows from one region to another without impacting the rest of the network. And the one thing we can say about all of these results is they will all be wrong. Our goal is not to exactly predict the future. When we do our analysis at NREL, we focus on identifying trends and relative changes between scenarios, rather than emphasizing absolute numbers. For example, if we look at these plots and focus on the orange color, which represents investments in battery storage capacity across different scenarios, we see significant variation in the amount of batteries being built in each scenario. Investments in batteries increase in the BESS 50 and PV 50 scenarios, where we assume capital costs for batteries and solar PV respectively decline faster than is currently projected. On the other hand, if capital costs for wind decline faster than anticipated, represented by the wind 40 scenario, we don't see a similar increase in battery investments. And so by comparing scenarios, we can better identify some of the drivers for different investment trends. And there are many more results that can be extracted from the model, including the location and time of anticipated curtailment, capacity contributions from different technologies, including capacity credits from wind, solar, and energy storage technologies, plant load factors, expenditures on capital costs, but also operating costs, fuel consumption, emissions, and the impacts of different policies. As I mentioned before, ReEDS has evolved over time to answer emerging questions. ReEDS is particularly useful to answer questions related to the drivers of power sector change. For example, how specific policies, regulations, technology cost and performance, or fuel prices may impact future generation and capacity mix. There are some things the model is not designed to do, including detailed production cost modeling, including unit commitment and economic dispatch decisions, and AC power flow. Though some of these are heuristically captured outside of the optimization problem using hourly data, and others we're trying to improve. To give you some examples of the types of questions we're using ReEDS for today, we're looking into how would changes in the load shape impact generation and investments in the mid to long term in India, and how would increased flexibility in India's coal fleet impact investments in energy storage and gas technologies. The ReEDS model has evolved over time and will continue to do so, and we will continue to roll out model improvements as they are developed. Some of the things we're working on this year include adding more candidate storage technologies to include different duration batteries, improving how we estimate the energy value of storage with a new module that does hourly optimization of energy storage dispatch, adding new hybrid technologies as candidates, including different combinations of renewable energy and storage, improving how we estimate the cost of developing location-specific resources, such as wind and solar, with updated resource supply curves, improving our reporting on electricity costs to consumers, and adding more weather years to improve our estimates of renewable energy availability and generation. And as a final note on this overview of ReEDS, we want to make you aware of how you can stay engaged. First, you can join our mailing list at reeds.inquiries@nrel.gov. Here you'll get information about new publications, group meetings, model updates, and events like this webinar. We'd also encourage you to attend one of our group meetings, which we're just starting. The first one will be next month, July 9th and 10th. If you follow the link on the slide, you can look at the agenda and register for the meeting. This first one will be a virtual meeting. In the future, we do hope to have in-person user group meetings as well. And also, we would encourage you to follow the ReEDS GitHub repository. This is where you can access the model code, as Ilya will explain later, and stay up to date on issues with the model, fixes, and new releases. So before we transition to how to access and run the model, I want to pause for a few minutes and take any questions that may have come up.
Hi, Amy. I see some good questions coming in, so I'll help just to moderate some of the question and answers. I just want to encourage everyone who's listening in to please submit questions through the questions pane. And if there are questions that we aren't able to address, we'll be happy to follow up over email. So the first question, Amy, that we have is, what is the temporal and spatial resolution considered in the ReEDS model?
Sure. So we model, every year, we represent the year with 35 time slices or representative hours to capture different times of year, so different combinations of electricity demand, but also renewable energy availability. So we've divided the year into 5 seasons, and then within each season, we have 7 representative times of day. So that would include sunrise, sunset, morning, evening, a peak demand, an afternoon, and then a nighttime time slice.
And another related question, maybe you can elaborate a little bit on how you are modeling renewable energy plants. Are you aggregating them, and what is the representation?
Sure. First, let me answer the question about the geographic resolution.
Sure.
So we've modeled every state and union territory as a single node. And so how many nodes would that be?
34.
34 balancing areas. And then within each balancing area, so within a particular state, we've also divided that state into smaller geographic areas we're calling resource regions. And we model wind and solar at the resource region level. So all of India is divided into 146 resource regions. And so this actually feeds into the question about how we represent wind and solar. We do aggregate. We don't model individual plants of any technology. So we do kind of aggregate the capacity, but we're capturing the generation from that resource region level. So there's 146 locations where wind and solar could be built. And we have detailed resource data for each of those locations. And so then we can get the generation from each of those areas.
Thanks, Amy. So another question came in about whether this model can be used for distribution planning.
Right now, we don't use it for distribution planning. I think there are really good tools available. Some are open source for distribution planning. This one, ReEDS is really focused on bulk power system planning.
Okay, and there's a question about the computer requirements. I think that we'll be getting to that in the next section where we'll do a demonstration. So I think I'll skip to the next question, which is regarding what are the assumptions for batteries and how we model batteries, and what assumptions do we make for battery costs?
Okay. For all the specific cost data, I would encourage you to check out the paper that we have in the slides that all of the images came from, because there you can find all of our model inputs. As well, once you access the GitHub repo, you'll have access to all of our input data. So there you can look at all the costs. I don't remember the capital cost for batteries off the top of my head. But we do only look at a 4-hour duration battery. In the future, as I mentioned, we'll be implementing changes to have different options. So 1-hour duration battery or 2-hour and so on. But for the cost, we could look at the input files, which all the users will have access to.
Thanks. And maybe the next question we can address. Let's see, there are quite a few questions coming in. Are you modeling in ReEDS the transmission network fully, or at a regional level, and can you speak to how that is being represented?
Mm-hmm. So we don't do a full network representation in ReEDS. We model the carrying capacity between nodes. So in this case, it would be between states and union territories. So the country is 34 nodes. And there we took data on the actual transmission network and the carrying capacity of those lines and aggregated it so that it's just one corridor from one state to another. And as I mentioned, we're not doing AC or even DC power flow. So ReEDS is useful as a first pass to identify trends and where investments could take place and trade-offs between having to reinforce the network to add more carrying capacity versus building generation in a different area. But it certainly needs to be complemented by more detailed power flow analysis.
So I think we have time for at least 2 more questions. The next question I think we'll take is, what are we considering for forecasting load and the capacity? How do we forecast both?
So for load, we use CEA's EPS for our load forecast. We did, because it doesn't go all the way to 2047, we did make some assumptions that their last 5 years of forecast would just continue out to 2047. And we had hourly load profiles for every state as our for 2014, and so we use that using CEA's forecast to project the load out and how it would evolve hourly out to 2047. For capacity, this is new generation capacity. I'm guessing.
Yes, the question is about how do we forecast capacity.
Mm-hmm. So that was again based on input from CEA and published documents from CEA on projects that are in the pipeline. And then we had information on planned transmission additions from POSICO.
So another question is regarding emissions and whether we can consider emissions in the model.
We do model emissions, only carbon emissions, and we track them, but we don't have any emissions constraints. It's certainly something that can be implemented in ReEDS, and in the US version of ReEDS, there are quite a few emissions regulations that they include as constraints. But in India, we've just tracked the emissions.
So I see another question about the battery costs. I think that we'll refer you to the report. So I think that there's one clarification that we can make, that battery and BESS are the same. So BESS stands for Battery Energy Storage System. Okay, and I guess we'll take one more question for Amy. whether pumped hydro is considered and whether you see any trend for pumped hydro investments.
Pumped hydro is considered. We have the existing pumped hydro included in the model, assuming a 12-hour storage capability. And then there's the option to build more hydro, as it's a candidate technology. We don't currently see hydro being built economically, but we could. It's something you can play with, the different storage requirements, and see if under what conditions pumped hydro might get built in the future.
Great. Thanks everyone for your questions. I encourage you to continue to submit questions. We will be doing another round of Q&A at the end of this webinar. In the meantime, I think we'll transition over now to the demonstration. So thanks, Amy.
Thanks.
Great, so we had some questions about requirements for running this model. And so what I'll start with is just to talk a little bit about what you need in order to get started. So ReEDS is an open access model, which means that all of the code base is available to view and edit. It is not open access, so there's a distinction there between having public contributions and being publicly openly accessible. But you can use the model as you see fit once you do have access, and access can be requested on the website, which I will display in a moment. So the computer requirements for ReEDS, you do need, although there is no license fee for ReEDS itself, you do need a working GAMS license. So GAMS is the algebraic solver. You need to have Python and R installations, which are open source and are free to download and install. You also need a GitHub account and some familiarity with using GitHub. As far as the computer requirements, we recommend to have at least 15 gigabytes of RAM, of memory available. And 4 logical processors in order to allow the model to solve in a reasonable amount of time. So as I'll show you, it is quite flexible. So if you only have a small number of processors, you can scale down the problem in order to solve a smaller number of years. Although for a really long horizon and for a large problem, we do recommend more logical processors. So up to 32 or 36 cores is what we use here at NREL. So I think I'll start by showing the website of where you can request access. So if you navigate to nrel.gov/analysis/reeds, and you click this green button, request access, then you will have access to the GitHub repository. So next I'll open that page. This is the GitHub repository. So GitHub is a free service, and you can create an account. Once you're granted access, you'll be able to log into this repository. And the master branch that I have open here is the US ReEDS model, which you will also have access to. And there are several branches. And so one of the branches is called India. And this is the ReEDS India model. Next, I'll open the ReEDS India model on my own laptop so that you can see how it looks once you have it downloaded onto your computer. So here's the folder structure for ReEDS. And you'll see that there are some lettered folders between A and F. So let's talk about those a little bit. A is the inputs folder. This is where we have all of our assumptions, all of our data that go into the model. B is the equations folder. So these are the GAMS equations that set up the objective function and all of the constraints of the problem. The C folder is where all the work is done for solving the model. The D folder is where we have our 8760 module, and I'll talk about that more. That is the chronological assessment of capacity value and curtailment. E folder is where we store all of the results. And F analysis is a module that we have provided that will visualize the results. And we'll look at an example of that. So before we get into the demonstration, let me talk a little bit about the concept behind how this model solves the problem of capacity expansion into the future. So we solve the ReEDS India model in what we call an intertemporal formulation, which means that this blue box on the left called the supply model is solving all of the years at once. So this is what GAMS is doing to solve the objective function for capacity investments and transmission investments for all years in the entire horizon. And it does that simultaneously. Once those results of the capacity, the load profiles, the performance characteristics of new built plants, and the transmission characteristics are then, those results are then passed to the 8760 module. And this 8760 module runs year by year. So if we're starting in the year 2017, it'll create a solution for that, then run the next year, and the next year until we reach the final year, which in our case is 2047. The results from that 8760 module are the capacity value and the curtailment calculations. So the capacity value specifically for wind, solar, and storage technologies, and the curtailment for wind and solar as well. And these results are then passed back to the supply model. And these impact decisions about what capacities need to be built in order to meet the planning reserve margin in the future. And the curtailment results impact decisions on what renewable energy is cost effective to build and what energy storage can be built in order to reduce curtailment levels, and what amount of energy storage is effective and cost effective for that purpose. So then we solve the supply model again, and we iterate this process until we reach a solution that we feel has converged. We typically run 4 iterations. In our testing, we've seen that after 4 iterations, we have very marginal differences from additional solve cycles. So let's go back to the demonstration now. And I will start by going into the A inputs folder. And I don't expect you to remember every detail of this demonstration, so we are recording this webinar, and you will have it for future reference if you do need to refer back. So I'll open cases.csv. And cases.csv is the sheet where we store all of our input assumptions and for different scenarios that we'll be running. So let's start by looking at this description column, column B. Here we have some parameters for the model. So what kind of solver are we going to use? What modeling setup are we using, sequential or intertemporal? For the India model, we only run the intertemporal version that I talked about on the slide. And let's focus on this description, which is the set of years that are modeled. So now if we go to the next column, which is column C, we'll see that we're pointing to a spreadsheet, which is called modeled years set all.csv. So this is the spreadsheet that tells the model what years to solve for. And column C has all of the default values for all of the different parameters that we can have for the model. Now the next columns, columns D through L, are our scenarios. So we have a base scenario. And as you can see, The base scenario typically uses all of the default values. We can also adjust the number of years and the horizon that we solve in the base case. Other columns include our scenarios. So we have a new gas scenario where we change the limits, the fuel limits on what gas fuel is available. We have different cost scenarios for batteries, for solar. We have a scenario for coal flexibility. So the coal flexibility scenario, you'll see in this column, we have a different spreadsheet that we point to for our minimum load fraction or minimum generation constraint for coal. Then we have some scenarios on load forecasts. So whether the load will be less peaky than is under the base case, or whether load will grow not as quickly as in the base case. And we have a scenario about the planning reserve margin. So if we assume no planning reserve margin going into the future, that may affect what capacities are built. We also have this toy model, and this is typically used for debugging if you're testing new capabilities. So I think what I'll do for this demonstration is let's add a new scenario and see how to run it. So I'll add a new column called webinar. And let's keep all of the default values. The only thing that I'll change is the number of years that I'm running. So I will change the modeled years set to modeled years set webinar. Okay, we've created a new scenario, and now I can close cases.csv. Now let's go into the inputs folder and go into the folder sets. So these sets are all of the inputs again, as I mentioned. And you'll notice here that we have this spreadsheet called modeled year set webinar. So I've created this in advance. Let's open it and see what's in here. So here we have a subset of years between 2017 and 2047. And as I mentioned before, this is one way in which to reduce the size of the problem while still getting useful results. We can run the model for just either every other year or skipping 5 years or skipping 10 years. It's flexible in that way, and that will reduce the number of cores that you may need to solve the model in a reasonable amount of time. So let's open up another spreadsheet. I'll go back. I'm in the inputs folder, and let's open up the generators folder. So here you'll see a lot of the inputs for the generation characteristics and the choice of generators that we're giving to the model in order to choose between. So if I open this data conventional CSV, and I'll look at the first series of numbers. So the first column shows the year. So these are the years that I'm modeling between 2017 and 2047. Second column is the technology. So the first technology is battery. And so now we have the capital costs, and these are capital costs in Indian rupees. We have the cost of fixed operation costs, and we have the variable operation and maintenance cost. Then we have column F, which is the heat rate. So batteries, they don't have a fuel, so they don't have a heat rate. If we go further down the spreadsheet, we can see that gas technologies have a heat rate, which is a measure of their efficiency in fuel consumption. So if we wanted to make changes to this spreadsheet, we can create a copy and add it to one of our scenarios. So I'll close this now. Let's go back to our main ReEDS folder. So one more thing that I'll mention before we run a demonstration is that we've provided an easy install version of ReEDS. So the easy install version of ReEDS, it will install all of the packages, including R and Python and the GANs the GAMS program, it will do that automatically for you in the background, and then you will see this folder structure. So the instructions on how to install using the easy install feature are available online on the GitHub repo in the branch called India Easy Install. And you can go down here and follow the README instructions. Okay, now for the fun part, let's run a demonstration. So to run the model, I'll open a terminal, and I've navigated to the directory in which I have my ReEDS model. Now, the only thing I have to do to start this is to type Python run model.py. So the first question that you're asked is, what is the name of your run? So we'll name this run web demo. Then you're asked, what scenarios do you want to run? So we can choose to run all of the scenarios. Here, this is option 10. Or we can choose any combination of scenarios by adding numbers with commas. So for example, if I wanted to run the base case and the webinar case, I would write 0, 9. In this case, let's just run the webinar scenario. So I've selected scenario 9. The next question is about running iteratively. So as I mentioned before on the slide, we're first solving the intertemporal problem, which means that we're solving all the modeled years at once. So the model is making decisions about what investments to make in 2022 and 2023, as well as what investments to make in 2047 and 2046, and so on. And it's making those decisions simultaneously. Then we'll pass those results into the 8760 module. So this question is just asking whether we want to use that 8760 module, and I'll say yes, which is also the default. The next question is about where is the GAMS path executable. So by default, this should be installed correctly, so I'll use the default. The next question is asking whether we want to compile all of the inputs. So you can choose whether you want to compile all of the inputs if this is running for the first time. If not, if you've already done this before, then you can skip this step if you're testing how the model will solve. The next question is asking whether you want to run the model. So do you want to create a solution? This is useful as you can say no, and you can just compile the inputs if you just want to view that all of your inputs are being compiled correctly. So I'll say yes, we do want to run the model. And the final question is asking whether we want to run the visualization that we've provided, and I will say yes. Okay, now the model is running, and we just have to wait. But I've done this in advance, so we won't make you wait. I will show you what results you get at the end. So let's first start by opening eOutputs. Sorry, let's go back. We'll open fAnalysis, and we'll view these results. So at the end of the model run, you should be able to see the results in this format, which is an HTML file, which is also easy to share. So the first set of results is about firm capacity, and we have a plot and the data that goes with it. We also have the capacity results. So as you can see in this demo that I'm displaying, it does not have every year between 2017 and 2047. It is skipping years every other year, which allows you to run the model faster and generate results. We also have information about annual generation numbers, the generation mix as it evolves over time, and other important results. So we also have maps in this analysis script that show you where the wind and solar is being built. And as mentioned, as Amy mentioned, we have 147 resource regions. And using these maps, you can see specifically where the ReEDS model is deciding that wind and solar are built most cost effectively. We also have information about transmission investments and power flows. So one other thing that I'll mention is that these results are fully available to you when you run the model, and they can be accessed and manipulated as needed. So you are not limited to the results that are displayed here. So with that, I think that we'll end the demo there, and happy to take questions.
Thanks, Ilya. We do have a question about batteries and what types of batteries are being modeled, if we're doing rooftop PV batteries, if these are lead acid or lithium ion batteries.
Yeah, good question. So the battery cost assumptions that we are using are assuming a grid scale lithium ion battery. And at the moment, the ReEDS model, as Amy mentioned, only has a 4-hour battery. So we're assuming costs for a standalone utility scale lithium ion battery.
And then there's a question, will the model data be available through the Git repo, and what are the terms governing the use of the data?
Yes, so the data is available through the GitHub repo. We are not sharing anything that is proprietary, so all of this data has been developed through analysis at NREL. There is a restriction on publishing, so you would need to make sufficient reference to NREL and to the ReEDS model in order to publish based on this data and on the ReEDS model.
Okay. Another great question about what are the operational constraints of thermal plants that we're including?
Sure. So we do have a reduced form representation of dispatch. And so we do have constraints on the minimum generation levels and the ramp rates, the maximum ramp rates of thermal plants. However, these are just approximate dispatch representations, and it does not capture the full intertemporal and chronological constraints that thermal plants do have. So to look at those kinds of questions in more detail, you would need to run a detailed production cost model, so a dispatch simulation, which we do not do. But we do have sort of a time slice approximation of those constraints.
Does the easy downloadable version work on Mac as well? And how is the compatibility of ReEDS with Macs?
So that we do have a US ReEDS version that's currently compatible with Mac. We haven't done extended testing with the India model, but that is currently being actively developed.
I should say I'm a Mac user and I use the easy install version, and I have no problems. So
good.
Okay, so another question, just clarifying the operational constraints of thermal generators. So the ramp rate is being aggregated?
That's right. Yes, the ramp rate as well as the minimum generation are being aggregated for each technology.
Okay, great. What platforms are you using? What programs are you using for the visualization?
So we use R Markdown, so that's currently being visualized using R. The US ReEDS model uses Python for their visualization, so bokeh. So you would have access to that code base as well.
And for those who have their own kind of favorite way of doing visualizations, you do have access to the raw output data, so you could write your own scripts as well. For the new build out of hydro, do we need hydrological data?
Yes, you would need information about capacity factors for hydro. So we've relied on historic capacity factors for existing hydro plants to represent hydro in the future.
Okay, great. So ReEDS India does not model EV load. Why is that?
Yes, we've taken a scenario approach to modeling load because load is an exogenous input into the model. So we've done load forecasting into the future based on CEA projections, as Amy mentioned. And we've included different scenarios in the load shape. So one of those scenarios can be increasing penetration of EV loads. So that is not solved in the model, but we do have a way of approaching questions about EV load.
Does the model have two separate models, so linking supply and capacity?
No, I think I understand that question. So the model is solving simultaneously the need for capacity and the need for energy supply. So we have different constraints about energy and about the need for reserve capacity in order to keep the system reliable. And those constraints are being solved simultaneously.
And this one, you may or may not know, but what's the difference between the LEAP model and ReEDS?
I'm not familiar with the LEAP model, not in detail.
My LEAP, I've never used it, but my understanding, this models the whole supply chain for energy resources. So you're looking at extraction, production, and then consumption for all different energy resources. Whereas, and it's kind of tracking those along the way. ReEDS is really focused on the electric power sector. It's a least cost optimization for building out the electric power sector. So we're not looking at, for example, having to extract the coal and transport it to the plants. LEAP captures all of that. So they're very different scopes of what those models cover. And then I was wondering if you could speak to, there was a question about what is intertemporal versus sequential. So maybe we could touch on that, and also maybe some tips for how to make the model solve faster using the intertemporal.
Sure. So in the US ReEDS model, there's an option between solving sequentially and intertemporally. And the difference is that in a sequential model, you're solving 1 year at a time. So if I'm starting in 2020, I'll solve the capacity mix for this year, and then I'll pass that result to the next solve. So I'll solve 2020, and then I'll separately solve 2021. In some ways, that makes it faster because it is faster to solve 1 year at a time. One of the downsides of that is then your model does not have perfect foresight of your forecast or your load forecast and your costs. And so your model may not be making optimal decisions based on current projections of costs and of load. The intertemporal solve, as I mentioned, is a different approach where the model looks at the entire horizon and solves the problem simultaneously for all years. It does take longer. In most cases, it takes longer to solve it intertemporally. But we believe that this is a good approach for the Indian context. And
I would just add a small thing, especially when we're testing, and we use the intertemporal mode, we don't actually include all of the solve years. So we'll skip and only model maybe every third or fourth year. And because you're assuming perfect foresight over the whole horizon, you get pretty much the same answer or result as if you had modeled every year, but it does solve faster that way. Okay, so we only have a few minutes left, so maybe Ilya, if you want to kind of touch on what's coming up next.
Sure, yeah. So our next modeling spotlight for NREL's models is coming on July 15th, so I encourage you to participate in that as well. And we'll be presenting on the eMERGE tool. It'll be a different team at NREL who are presenting a tool that they have developed. It's an open source software that allows distribution utilities to model feeders directly from GIS data. And so it's really useful for computing metrics on DER scenarios and looking at the ability of storage and rooftop PV in order to improve metrics on the distribution system.
Great. And if we didn't get to your question, please reach out and we can follow up separately. Okay, well, thank you all for joining. I hope that this was useful, and yeah, please stay involved through the mailing list and join the user group meeting, and definitely request access to the GitHub repo if you'd like to start using this model.
Yeah, thanks everyone, and look forward to working with you if you are interested in requesting access.
Thank you.